Okay, can you hear me? Okay, so good morning, everyone. My name is Jędrzej Rochała, and I'm a software engineer at VirtusLab and Scala Center. So if you're wondering what is the relationship, VirtusLab pays me the money, and I work full-time at Scala Center. So my work is mostly about the compiler, Scala free compiler, and IDE implementation. So I want to share my knowledge about IDE today with you, and that's it. I also maintain Scasti, the online playground, so if anyone is using it, well, I'm the one you should report issues to. So let's begin the presentation and ask ourselves a question. So what happens inside the IDE? Let's go through 3 examples where we will try to reason what should happen to provide you the results. So the first example will be a completion. It's a very simple snippet where we define a case class test with 2 fields, field A, field B. We then instantiate the test and assign it to value X. And finally, we want to run completions on it. So what needs to happen to return field A and field B as a completion result? So there are a few things. First is we need to know the position we are at. It is very simple. Editor can return this. This is the position of the cursor. The second thing is that we need to know what are we running the completion on. So we can do this very simply. We can just split this last line by dot, and we can take the head. It will be X. And what is next? We should try and find this X in the context, in the snippet, and then find the type of test so we can access its members. So how would it be done in the compiler? So code is internally represented as a tree. We need to parse it into those trees, and then we need to run a type checker. And the side effect of this type checking is a context, is a state of the compiler. And we will use this state to basically query for the proper symbols. So in this example, when we ask for this completion, we basically will go up. Please tell me what is X. It will return X is a symbol. It's a definition of a value. OK, but what is the type of X? It's test. OK, give me the members. And here we should have the completions. Let's go to the next example, hover. It works just the same. We find the position. We are hovering the value X, and it should find the type of X and the documentation, and then display it to you as an end user. Another example, go to definition. Once again, we need to parse the code, type check it, and find the definition of test. That's it. And the list can go on and on and on. Most features are implemented like that. So right now, let's wonder, it was a very simple example, and it is not that hard, actually, as you just saw. So what is actually hard about creating an IDE? I would like to first split and explain what IDE means. So IDE stands for Integrated Developer Environment, but underneath it is actually an editor plus language support. And it can be bundled together or separately, like IntelliJ is bundled with Java support and editor. And you have VS Code, which you can plug metals into. So that's it. And they can't be used without each other. So to have IDE, we need to implement both. And both are extremely hard to implement. Starting with editor, which is known for its famous I/O operations. It has to be super performant in order to not be laggy. No one's like sluggy environment. It also has to implement some interactive features, like one way is to return the completions, and the other problem is to display them. We also have to implement the debugger and everything, so the list can go on and on and on. Editor is basically a very complex piece of software. And what about the language support? It depends. And there are many factors which can influence how hard is it to make a language support. So let me go through a few of them. And the most important one is language syntax and its complexity. So on the left, we can see we have the Python code, which has very few building blocks. we can't argue that Python has more complex syntax than Scala, which is known for its implicit conversions, extension methods, refinements, and the list can go on and on. Scala has way more complex syntax, and with the more complex syntax, well, we have to handle each of these cases. So with more cases, the code gets more buggy, it is harder to reason about, it just gets harder overall. So next thing could be a dynamic versus static typing. So in the left example, where we define a method without types, what should be the completions for A? We have no clue. And there is really no way to tell what should be the completions for A, because IDE can't read your mind. In the second example, you have to type check the snippet to know that it's a number. And this number can be defined in your snippet, it can be defined in library, or even it can be, I don't know, a different library. So next part would be an interoperability with other languages. This is also something which is not unique to Scala, but we have to implement support for Java, and it is not so trivial, especially with type erasure and, well, all that stuff that... Last thing would be a frequency of language changes. IDE needs to support the latest features to provide the best experience for you all. So the more frequent changes we have, the more work we have. And recently in Scala, we had this big migration to Scala 3, where we introduced fewer braces, which is a new braceless syntax, and we can write map without colons, braces, I mean. And also we replaced implicit with using, so it seems like a very simple change, but actually, if you have custom parser and custom type checker, it is not so simple to handle this. So let's go back now with a thought to the first examples I've shown you before. I mentioned that we need to parse the code and type check it. So this is common to almost every language support we have. And let's compare how different IDEs do it, because everyone has better IDE than us, obviously. So let's start with Python. Python uses a built-in parser. It is part of AST module, and it has a custom type checker, which is basically a heuristic over type hints. Rust Analyzer, which is the language server for Rust, uses custom solutions for both parser and type checker. But previously they used compiler type checker and compiler parser. They changed it recently. We have TypeScript, which is also using compiler, parser, type checker, Golang the same. Kotlin also uses compiler, parser, and compiler type checker. Then we have IntelliJ Scala plugin, which uses custom parser and custom type inference engine. Then we have Metals and Enzyme, which uses compiler parser and compiler type checker. So why am I telling you all of this? Basically, there is a big difference between both approaches. So custom solution allows you to do very quick and easy changes related to optimizations. You can basically hack your parser around, hack your type checker around to make it super fast, and so you will get your results faster in your IDE. In the built-in parser, built-in type checker, you have to remember that this is actually a real parser and real type checker. So it still has to compile code safely and type check it safely. So it is way harder to hack it around. It can be done, obviously, but it is just harder. So secondly, the custom solution has to be maintained by us. And well, that's another work that you have to be doing instead of relying on compiler team, which would update the parser and the type checker for you. Why should we care? Then we have, like, in my opinion, the biggest difference. The results may diverge from the official language type checker. So there is no way to basically re-implement type checker and have one-to-one relationship with the compiler, with the original one. It is so complex piece of software, especially when we don't have specification for a typer. It's almost impossible to replicate the same behavior. So you can then expect errors where your compiler has different outputs than your IDE, and this is not nice. Basically, these are false positives. Well, and as I said, it basically requires more resources. So that's it. I will focus on metals today because they use the solution I'm working on. So I can tell you more about it. But for those of you who don't know what is metals, metals is basically a language server. And language server is something which was created by TypeScript. It was created especially for VS Code. So they can have good IDE integration with some protocol, basically. And Scala also uses BSP to communicate with build tools, which is also another protocol. And it is necessary in order to ask your build tool to compile the code or run it without caring what build tool you have. So BSP is getting adopted more and more. Few weeks ago, Gradle has added BSP support. So, well, this is our protocol. We created it. But if you want to know more about the metals and its integration with VS Code and BSP, you should check out the metals lead presentation. It was actually presented here on the first edition of Art of Scala. But feel free to check it out. It has a very good explanation on how your IDE communicates with editor. But I'm not going to talk about that today. We are going deeper. So we will go directly into the presentation compiler. So what is the presentation compiler? Well, the definition changed throughout the years, but my understanding of it nowadays is that it is basically a wrapper for a compiler designed to be used by IDE, which also provides us with high-level API for those IDE features like completions. So the API basically looks like this. It's a subset of language server protocol, and it allows you various operations: completion, signature help, rename, definition, type definition, extraction of the method on converting to named arguments. The list can go on. It can be extended, obviously. So now a bit of history. So in May 2009, first presentation compiler was created. It was created for the first Scala IDE, which was called Scala IDE, and it was a plugin for Eclipse. So is there anyone who has used Scala IDE? Oh, nice. It was a breakthrough because it added a support for Java, interoperability with Java. So 3 years later, there was a first commit for Scala 3. And Scala 3 is basically a rewrite of the compiler with the knowledge people gathered by writing Scala 2 compiler. So it was created with IDE in mind and with better macros, and overall, it has better architecture. So 5 years later, the first support for IDE for Scala 3 was created, and it was done by Guillaume Matre, which was the PhD student of Martin's. So 3 years later, in 2020, Metals officially started supporting Scala 3. And how it looked like? Basically, it was the oldest trick in the programmer's book. It was copy-paste. We just copied the presentation compiler from Dotty and moved it to Metals. So at that moment, we deprecated Dotty language server, and Metals became the standard basic IDE for the internal compiler development. So that's it for the history for now. And let's go and see example implementation of some methods. So I have shown you previously how hovers work in this very abstract example. Let's go a bit deeper, how actually code looks like in your IDE. So this code, it takes params, which is basically a position and the URI of the file you are in, something which is provided to us by editor. So then we are doing some steps that are required to continue. So first we create some Java URI from the string. Then we run method driver for this URI. And what is a driver? Driver is a wrapper for the compiler. It is something that allows us to compile the code. And this method has a side effect. it compiles the code underneath. So by running driver for, we already have the context, which is shown in the next fourth line. And then we create some DTO for position. Then we have to extract the trees. And as I mentioned before, the internal representation of code is abstract syntax tree. So this is a normal procedure where we just extract your parsed code and type-checked code. Then we calculate something called path. Let's not delve into this. Then we calculate the type. And then we find the enclosing source symbol, which we then modify to display it in your IDE. So let's go to the next definition, completion. The steps are the same. We create a driver, we have the context, which is the state of the compiler, and we basically run a method called completion.completions. So I skimmed over those methods because, well, it is another compiler. So we have to delve even deeper. So in order to know what is interactive, we have something called interactive compiler. So what the heck is this present interactive compiler? So this is the actual compiler that runs your code for your IDE. And it has to be a very specific compiler. It has to be asynchronous, it has to be interruptible, it has to be targeted, and it has to be very, very fast. So why it has to be asynchronous? You can send multiple requests basically for your in your IDE, so they have to be handled asynchronously. Why it has to be interruptible? If we send 5 requests for completions, we don't care about 4 previous ones. We can just skip them because the latest one is the valid one. Then it has to be targeted. We shouldn't recompute stuff that doesn't need recomputing. And to be fast, we run it only until type checking. So there are only 4 phases of the compilation run out of 27. So basically a front end, and all of those other phases are dropped. For a few reasons. One of them is performance, and second is the transformation of trees breaks your IDE. You don't want to work on transformed trees because this is something that you don't see in your IDE. You see untransformed trees. So the implementation of interactive compiler is basically it's a subtype of the normal Scala compiler. It just extends it and overrides the phases. So, well, it is the exact same compiler, but shorter. And interactive driver, well, as I said, it's a wrapper. It allows us to extract those trees and to run. It's not important. But the interactive, this is very important because those are the building blocks of the IDE implementation. So with those, we can basically achieve all the features we already have. So we were used previously enclosing type, enclosing tree, enclosing source symbol, and path2. So let's now use those building blocks and go step by step through different compilers, like a debugger, and see how your completions are actually computed. So once again, we have this very simple snippet where we define a case class test with field A and field B. And we instantiate it and assign it to X. And then we run the completions. First method which is run is the entry point of the language server. We have already seen this method. And, well, we get the driver, we get the context. And then we run this method completions. So let's delve into it. Let's step into this method. This method is implemented directly in the compiler. So, well, it has to be used with a specific Scala version. So the first step in this method is calculating path. We saw path previously in hover, but now again, we are recomputing this for the completion. So let's see actually how the path is computed and what is this path. So if we have this snippet and we want to find a path for this query, we want to find a tree at this position 86. So in order to do this, we have to basically step over the tree, over the thickets of this tree, and collect the trees we enter to. So first, we'll go into this package, we'll check the position 86, and the package definition has the span of 0 to 86, we can step into it contains the span we are looking for. Then we can go further. We have this members of those package. So first member is a definition of the case class. It has span from 17 to 60, so it doesn't contain our span we are looking for. We can skip this. The same goes here, the same goes here, the same goes here. And finally, we find the span we are looking for. So we have to now collect the members and reverse the list. Why reverse it, I will tell you in a second. But first, I want to say that the code you see below is basically a code after those 4 phases. It gets transformed a bit. Yeah. This is the query we had, and this is the path. So the first member of the path would be xphi. The next member would be a package which encloses this with this selection. So in the middle row, there is a pretty printed path, and on the lowest row, it is the internal representation of this via the case classes. So we can go further. We have the path right now. So let's find the context. We need to find the context to know the scope of the completions we are in. It works basically the same, so let me skip this and go to the next step where we compute completions. So first step is some edge case handling. I don't want to delve into this. Then there is something important. We have to decide whether we are completing the terms or types. So it doesn't get mixed up. We want only types when you want to define a type, and we want terms otherwise. So we also have to get the prefix so we can filter the completions. And the prefix here is just a phi. And finally, we can compute the completions. But how we compute them depends on the path, because we have different cases. In this example, we will go to the middle case. Our path was select of the ident x, where we selected phi, so the second case matches our use case. And the middle case is the selection completions. And selection completions is actually the piece of code that computes the completions. And in the beginning of the presentation, I have mentioned that complexity of the syntax can scale extremely fast. So in this example, we already have to compute the implicit conversion targets, and we have to find extension methods so we can populate completions with them. And I want to skip those. They are very complex, but actually, in the real example, it would find implicit conversions for this, like arrow association, which is used to create a tuple. So let's go into the last part, the direct member completions. So in this method, we basically collect, we have the type of this x, and we collect all the members of x. And then we have to basically collect only those which interest. So the first step would be getting this member, and then we will have to check whether the symbol is param accessor. Actually, this is param accessor because field A is defined in the constructor, and whether it is accessible from our scope. We return non-private members, or we return all members otherwise. So in this example, they are accessible, so we return member and all its overloaded definitions. So, well, we have populated the buffer, and we returned it. So we have the completions right now. Last step is the description of them. So they are pretty printed. And it is basically showing the name of the completion, the type of the completion, and returning some symbol for later use. And it should end up with something like this. So this is exactly what URD does. And this is only a compiler completions. We have way more layers of completions, like match case completions, index completions. So, well, this is a very simplified example, but I think you got it. So, what was the path we took? We started with metals Then we delved into presentation compiler. Then we went into interactive compiler. And finally, we were using the compiler internals, the compiler state, getting the members from type and all that stuff. So the repositories in which the specific modules are located are separate. So presentation compiler and metals belong in Scala meta metals, and interactive compiler and compiler belongs in Dotty. And there is a very, very big problem, because everything you have seen by now is an internal API of the compiler. So basically the internal API changes every day. So you have to use a very specific version of the compiler to get your interactive compiler. So, well, this has few problems. We still have this one-to-one relationship because of that. But we can also fix the bugs, because presentation compiler is located outside of the compiler. We can hack around this. We can do a special case for given version Scala. If Scala is less than 3.3, we handle something differently. So we can basically fix bugs in older version of Scala. But the problem is we are strictly bound to the version. And it is also released from another repository. So when API changes, we will only know about this change the next day when the nightly test runs. So it just wasn't good to maintain. And also some latest syntax and features weren't supported instantly. It was just annoying. So we have started an initiative called a stable presentation compiler. So what we did is we basically moved presentation compiler back to the Dotty. So it is now released along the compiler. And well, it is way easier to work with this right now. So let's go back to the history. And now in the June, there was a commit which implemented this Scala-free presentation compiler, the stable presentation compiler. And once again, we did the old good trick. We copied it from metals. So we have the presentation compiler in Dotty, which is binary tested, binary compatible with MIMA. So if anyone wants to use it, he can freely use it without being scared of losing compatibility with it in the future versions. And this is the recommended way to create your IDEs right now, if anyone wants to. So what's the difference? The difference is that, as I've said previously, we now support every Scala version. And why is that important? So I said that it has the presentation compiler has to be released for a specific Scala version because of binary incompatibilities. The biggest problem was Scala compiler is released every day as a nightly. And also you can release it locally. And it was used a lot by the compiler team to debug the stuff. So they had no IDE support because of this, or they had delayed support because metals released it only 8 hours later or something like this. So right now, no matter which version of Scala you use, you will always have basic IDE support. So we still have this one-to-one relationship with the compiler. So each error is exactly the same as the compiler would return it. And we always support latest syntax, because if anyone changes the syntax, the CI won't pass. They will have to fix the ID first. So, well, this is not our problem anymore. The compiler API changes, the same thing. If anyone changes the API, someone in the compiler team who created this PR will have to fix this. So basically, we are offloading the work. And, well, the drawback of this solution is that iterations are slower because we are working directly with the compiler and there are guidelines. It is just slower. We can't hack so fast as we could in other repositories. And the latter drawback is that we can't bug fix older versions. I mean, we can, but it is very, very expensive and not worth it. And it may seem like a very big drawback, yeah, because what if I am using 3.3.0 and I won't have the latest fixes, the latest features, the latest support for IDE? And actually, this is not a problem, because in Scala 3, we have changed the release cycle. So basically, we now have the LTS line and Scala next line. So with the LTS, we guarantee a backward and forward compatibility. So you can bump your minor version you are supposed to bump your minor version, so you have your latest IDE support. And for Scala Next, well, the release also happens, so each bug fix to the presentation compiler lands first here, and then they are moved to LTS line. So well, this is actually not a problem. So that's it. I want to thank you for listening. I hope that you know more about your IDE right now. And well, I want to use this opportunity and welcome you to contribute to open source. And by contributing, I don't mean staying on the weekend and doing some fixes in the, if it's fixing some issue from the repository. There's other way to contribute. And this is something we are very, very missing. And this is basically the reporting of the issues. So in order to have better IDE support, better compiler support, we have started a few initiatives. So this is something that you will face as the end users. The first one is better error messages, better reporting. So in order to have better reporting, you have to report that some errors are very, very bad. They are unclear. They can be improved. And how to do this? You can find it in this QR code or in the Scala Lang website. So there were already 25 error messages which could be improved, reported to the compiler, 14 of which have been already fixed. So by doing this, we will have all better error messages, so better life. Yeah, and those are my slides. So thank you. Are there any questions? Oh, I can't see anyone because of light. Yeah.
Do you think that in the future all those completion mechanisms will be replaced by some kind of generative AI?
Oh, that is a very hard question. Well, Scala has a very, very strong type checker. So if we can leverage this type checker to use it along with the AI, for sure, why not? We are in the great place because with Scala, we can catch most errors during the compilation. And we can do this with other languages. I mean, with other popular languages like Python. You will know that something doesn't work only when you run the code, if you don't use type hints. So in Scala, when you are using some generative AI, we can leverage the compiler to verify if the code is correct or not. I mean, at least at the syntax and semantic level. Yeah. Okay, I guess that's it. It was faster than I thought, so thank you.